Okay, in this video I'm going to explain more complex multi-level models, still in case study 1, in which we are studying the effect of some variables on academic achievement. So in the previous models we only used the intercept of a regression, so we only used the beta 0, and we had a beta 0 without variability and a beta 0 with variability. And in the model with variability on the beta 0 was better than the model without variability, so we are going to keep that variability in the model. So the previous models with beta 0 only, then that effectively is estimating the means of each region, and if there is variability, means that there is a difference in the means. Okay, so now we add a predictor variable, which is study hours. So we want to see how study hours affect academic achievement. Now, so we've got a typical regression here with an intercept and a slope, which is the effect of study hours on academic achievement. So now the intercept being different is not, now the intercept doesn't reflect the mean of each study, but you are going to see that in all the analysis, the beta 0j's or the gamma 00 that the beta zeros come from, they will be close to the mean of the sample, and that is or the gamma 00 will be very close to the mean of the sample. Why is that? Because Jamovi, when we do the analysis with Jamovi, the default is that it mean centers all the predictor variables. So the intercept will always be in the mean of the outcome variable. So so typically in a regression, the intercept is not the same as the mean, but because we are mean centering, then it is. Now we are going to have now a slope, and in this slope, because we have a j, it seems that we are going to have a different slope in each region, but actually this is not the case. So the second part of the model is what we've seen before, our prediction of each value of academic achievement, each observation of each so the academic achievement of each individual. We use for our prediction a normal distribution with the mu would be the prediction of the model, now adding study hours, and then some variability in that distribution. Now this is as before. The beta zeros come from this deterministic formula, which is the mean, some fixed effect, which is close to the mean of the sample. As we saw, it's not exactly the same, but it's close to the mean of the sample, plus the differences between the intercept of each group with the intercept of the whole sample, and that those differences, we are not going to come up with 4 values, one per region. Rather, we say that these values come from a normal distribution, which the mean is this one, and some lambda, which is the standard deviation or variance of that normal distribution. So we are going to estimate lambda, and we are going to estimate in gamma 00. We are not going to pay attention to the u's or to the betas. Now beta 1j, we are saying that it's only one value. So even though in the model it seems that we are going to have one per region, In fact, we don't. We are going to have the same value for the 4 regions. Okay, so that's the model I ran with Jamovi. So I show you how I did it, and here are the results. Okay, so here is Jamovi. We go to linear models, mixed model. Academic achievement is the variable, dependent variable or outcome variable. We've got as cluster variables region. Now we don't need the ones anymore because we are going to have a real predictor variable, which is study hours. And we put it in covariance. So now let's go to, we've got fixed effects. We see that study hours is automatically added. And in random effects, we've got the intercept conditional on region, so that's the beta zeros. But as I said before, in this model we are not going to add variability to the slope of study hours. So we are saying that the effect of study hours on academic achievement is the same in all the regions. Okay, so we get here the results. The AIC is 6,868 rounding, and the estimates here is for the intercept is 50.18, and for the slope study hours is 0.627. So that means that for each increase of a unit of study hours, we are going to the model predicts an increase of 0.627 units of academic achievement. Okay, and this is here we've got the variance for the intercept and the variance for all the predictions of the model. So that's what we have here. The fixed effect 50.18. This is the intercept. This is the effect of academic study hours on academic achievement, and the variance of the intercept, and we don't have variance for the slope, and the variance of the predictions. But in Jamovi it says residuals, and this is the AIC with rounding. Okay, so now the next step is to add variability to beta 1. So we are going to have a model with variability. Okay, so that's now we've got a random effect model, because before we had a random component in the intercept of the regression, but we didn't have a random component on the effect of study hours on academic achievement. So now we add that. So basically this formula is the same. This one is the same as before, this one is the same as before, and this is new. So we've got for beta 1s, we are going to have 4 beta 1s, 1 per region, and that comes from a fixed effect, which would be sort of the slope of, which is shows the effect of study hours on academic achievement of the whole sample, plus the difference between each slope of each region and the slope of the whole sample. But as I mentioned many times now, we are not interested in getting these 4 values, and we are not going to use these 4 values. We actually going to say that these values come from a normal distribution with this mean and some variability, which we use the Greek letter tau to represent that variability. So we are going to be interested in this value and this value, so fixed effect and the random component, and So we are estimating much less parameters than if we calculated all the U1s and as before all the U0s. Okay, so let's see how we do this in Jamovi. So we've got the previous analysis here. So the only thing we need to do is to add the study hours, the effect of study hours on academic achievement. We want the variability among regions. So we add that as a random coefficient or random effect. So we put it there, and Jamovi will calculate the values. So there is a reduction of only 4 points in AIC, so not a great reduction, but it's a bit better than the previous model. We've got for the so it means that the effect on study hours on academic achievement is slightly different in the regions, in each region. So it's not exactly the same, but it doesn't vary too much. Okay, so we've got that for the intercept, the fixed intercept is 50.21, and the effect of study hours on academic achievement for the whole sample is 0.645, and the variance of the intercept is 2.24. The variance of study hours is 0.0038, and the variance of each prediction is 17.55. So as you can see, this total variance is going to reduce. So the more variables we add, we expect this variance to go down because our prediction is a bit better. So if our prediction is a bit better, the normal distribution to make that prediction will have a lower variance because we are closer. So in order to capture the actual values with our prediction, because our predictions are closer and closer to the actual values, then we need a normal distribution with a smaller variance. Okay, so let's show this in the slide. So basically these are the values. The fixed effect of the intercept is 50.21. The effect of study hours on academic achievement is 0.645, and we've got the variances for the intercept and for the slope of study hours, and the total variance and the AIC. So now we are going to add 2 more predictor variables. So the next model adds 2 predictor variables. Here they are. So the model is, this is as before, this is as before. Now we've got beta 2 intelligence, and beta 3 the sex of the participants, and this formula is the same. Now for the intercept, that comes from a fixed effect gamma 00 plus the differences in the intercept among regions. For the effect of study hours, that the effect of the whole sample comes from the fixed effect plus the difference between the slope for each region and the fixed effect for the whole sample. For intelligence is the same. We've got a mean effect of intelligence on academic achievement, and these are the difference between the effect of intelligence on academic achievement in each sample against the mean fixed effect, and the same for sex. So the effect of sex on academic achievement, the variability among regions. and these are the distributions. The lambda is for the intercept, the tau is for the slope of study hours, the nu is for the slope of intelligence, and the pi is for the slope of sex. Okay, so let's do that in Jamovi. Okay, so here is Jamovi with the previous model, and so what we need to do is simply add the variables intelligence and sex. So let's do that. Let's find the variables. Intelligence goes to covariate, and then sex goes as a factor. Now, as fixed effects, we've got the three fixed effects, and now we need to add the random effects. Sex, we want to know the variability among regions, and intelligence, also the variability among regions. And then Jamovi will calculate that. It will take a bit of time, so I'm going to pause and then continue. Okay, the pause wasn't too long, just a few seconds. So we've got an AIC of 4,875. The estimate of the intercept is 50.05. The effect of study hours on academic achievement is 0.616. The effect of intelligence on academic achievement is 0.302. And so that means that for each increase in 1 unit of intelligence, we expect an increase of 0.3 units of academic achievement. Now, this may seem a stronger effect than the previous ones. So basically, from passing to the mean academic achievement to males, and we increase 0.7 points of academic achievement. And if we pass from the mean academic achievement to the mean academic achievement of females, we reduce 0.756 units of academic achievement. So as you can see, the range between the two genders is 1.5 or something, which is very small. So this may seem a stronger effect than the other two cases, but this is not the case, because intelligence has a range of, let's say, from 50 to 200. So it has a range of 150 possible values. Study hours also has a range that is quite large. Sex has a range of 1, so you go from one value to another one. So that's why you need to interpret this estimate taking into account what's the range of the variable. So if the range of the variable is very large, then even a small number as the estimate could be very important. And the opposite is true as well. So if the range of the effect of the variable is very small, like in this case it's just 2 values, then you need a very, very large number here. Otherwise, it wouldn't be important. Okay, so the opposite to sex would be region income, which has a much large range. It could be from $0 to, let's say, 200,000. So that a very small number as the estimate could still be an important effect. Okay, so the AIC of this model is 4,650. Now let's return to the slide, but I want to tell you something important here. So here in this model we added the fixed effect of intelligence, the fixed effect of sex, and the random component of intelligence and the random component of sex. So we added 4 new parameters and we compare that with the previous model. So the AIC is lower, 4,650, but we don't know exactly what of these parameters added value to the model. So it could be that only one of those parameters, if we added only one of those parameters, the AIC was 4,650, and adding the other parameters didn't help at all, or it helped so little that the AIC doesn't change. Or it could be that 2 parameters are important, or it could be 3, or it could be the 4 parameters. So I let you investigate by yourself. Try simpler models than this one, in models that you add just intelligence, the fixed effect of intelligence, then a model which you add fixed effect of intelligence plus the random component for intelligence, and then you add the fixed effect of sex only, and then the fixed effect plus the random effect of sex. So this shows you that there is a bit of an art on doing multi-level. You have to do a lot of models and compare those models. Sometimes there is no rule for which models to compare. Sometimes you create rules, like for example, when I did the beta 0 first and I determined that the random component was important for beta 0, so I kept the random component in all the models. So I'm not going to analyze any model without the random component of beta 0. Now, this is a decision that you have to be explicit. You typically have to do it before running the analysis. But some people may find it that this is not a proper decision. So as long as you make your decisions explicit, and you justify why you use the models you used and not all the models, then you are being transparent, and other people may say, okay, I would do the things differently, but they cannot accuse you of trying to get the models that are for the advantage of your hypothesis. Okay, so now we are going to do the last model, which is a full model, and the full model looks like we'll add to these variables 2 more variables, which are the student to staff ratio, and that variable is measured at the school level. So the variables that we used so far are measured at the individual level or the participant level, and that students to staff ratio is measured at the school level. And then we are going to add another variable measured at the region level, which is the income of the region. So we are going to only have 4 values of income, 1 per region, and the students to staff ratio we are going to have only 16 values, 1 per school. But we are still going to analyze the effect of those variables on academic achievement. Now we have to think very well the random components, and I'm going to move to the other slide. The random components that we can have in that model. So as before, we have the intercept, and the intercept in the previous models we estimated the variability among regions, but now we can also estimate the variability among schools, which we didn't do before. We do the same with study hours. We study the effect of study hours on academic achievement and how that effect varies among regions and how it varies among schools. Same for intelligence. The effect of intelligence on academic achievement and how that varies among regions, which we've done before, and now we add how they vary among schools. Same with sex. The effect of sex on academic achievement and how that effect varies among regions and how that effect varies among schools. Now, for the and this is the variability of the prediction of the model. And now that we have a lot of variables and a lot of other the estimation of the variability among regions and schools, this should be much lower than in the previous models. And we've got one variability which is very important to explain. So, student to staff ratio is a variable measured at the school level. So, we cannot possibly estimate the variability of student to staff ratio among schools, because we are going to have only one value of student to staff ratio in each school. So you cannot study the effect of student to staff ratio on academic achievement in each school, because each school has only one value of students to staff ratio. But you can estimate the effect of students to staff ratio among each region, because you've got 4 values of students to staff ratio in each region, which is the value of the 4 schools that belong to that region. So you can study, okay, how much of student to staff ratio affects academic achievement in region North, how does it do it in region South and East and West. So that you can have a variability, but as I said, you cannot estimate variability among schools because you only have one value. And the variable region income, we cannot study any variability because we only have 4 values of region income, and we cannot estimate the variability among regions because in each region we have one value. So we can only study the effect of region income on academic achievement overall. We cannot see how that varies among regions. So basically the bottom line is one variable that is measured at one level. You cannot condition on that level or investigate the variability of that, the effect of that variable on the outcome variable in the level that you measure it. Okay, so I'm going to show you in okay, here is the full model in Jamovi. I did it and I ran it because this one takes quite a long time, could take 5 minutes to run, and so I show you what I did. Basically, I have academic achievement, I have the variable sex, intelligence, study hours, students to staff ratio, and income per region, and all as covariates, and I've now got cluster variables region and school. So for the fixed effects, we've got automatically they are added, all the predictor variables are added, and for the components you have to be careful because you cannot add all of them. So we've got the intercept among regions, study hours among regions, sex among regions, intelligence among regions, and students to staff ratio among regions, but we cannot have region income among regions. We have the intercept among schools, sex among schools, intelligence among schools, study hours among schools, but we cannot have students to staff ratio among schools. So that model has gives us all these parameters. So I'm not going to report all the parameters. I'll let you do that if you are curious. But we've got the AIC 4676 or 77, and so this is the result of the full model, and you can see here that the AIC is larger than the previous model, which was 4,650. Okay, so again, you need to maybe all the parameters we added are not adding to the prediction of academic achievement, and that's why we have a higher AIC, or maybe one of the parameters works and not the other. So again, you have to try different models and see which ones produce an increase in AIC, so you eliminate them. Okay, so this is the last model within the case study 1. In case study 2, we are going to see the application of multi-level models to experimental data.